Welcome to this presentation on Booth's algorithm. Booth's algorithm is an efficient multiplication method for binary numbers, useful for signed numbers represented in 2's complement form. So, in this session, we will explore the concept behind Booth's algorithm, understand its working through a detailed flowchart, and finally work through a complete example step by step. So the goal of this presentation is to not only show you the procedure but also to explain why Booth's algorithm is important in digital systems and how it improves the performance compared to the straightforward multiplication method. This is the flowchart of Booth's algorithm. So we have to load three key registers. The first is accumulator. The value of accumulator will be 0. Second is the multiplicand, and the third one is multiplier. And again the q minus 1 will be 0, and the count will be equals to the number of n. So number of n will be the number of bits present in the multiplicand or multiplier. Since we are taking in here 5 bit of numbers, the count will be 5. So iteration again it is 5. So the algorithm works by repeating a loop for a number of times equals to the number of bits in the multiplier, and each loop iteration we examine the least significant bit of q0 and q minus 1 together. So generally we have three cases here. The case 1, if the pair is 1 0, so we subtract the multiplicand from the accumulator. If the pair is 0 1, we add the multiplicand to the accumulator, and if the pair is 0 0 or 1 1, so we do nothing in that step. So after deciding the operation, we perform an arithmetic shift right on the combined AQ and Q minus 1. An arithmetic right shift preserves the sign bit, which is important because we are working with the sign number. So this loop continues until we have proceed all the bits. The final binary value is obtained by combining the accumulator and the multiplier register, and this value represent the assigned product in 2's complement form. Let us walk through an example to see Booth's algorithm in action. So we are multiplying two decimal numbers, which is 14 and minus 5, and these two numbers in within a 5 bit of number. So initially first is 14. 14 is multiplicand, so we have to write the binary of 14, which is 0 1 1 1 0. And since we have to calculate here minus m, so minus 14 in binary it is 1 0 0 1 0. It is the 2's complement of the minus 14, and the multiplier is minus 5. So minus 5 in binary it is 1 1 0 1 1. So again it is 2's complement of minus 5. So if we are multiplying 14 and minus 5, resultant we are getting here minus 17, and minus 17 will be in binary it is 1 1 1 0 So whenever we are implementing the Booth's algorithm, so at last the value of AC and Q0 should be minus 17, which is 1 1 1 0 Now we can see here how the Booth's algorithm will be implemented. Since we are taking the multiplication in 5 bit of numbers, so we have to perform the 5 iterations. Initially for the 0 iteration, we have to initialize all the values, and we'll see the pair of q and q minus 1. Since it is 1 0, so we have to perform AC equals to AC minus M. The value of AC is 5 times 0, and the minus M is 1 0 0 1 0. So the resultant we are getting here 1 0 0 1 0, and the Q will be same. So the value of 1 0 we are getting here, so we have to perform the AC equals to AC minus M, and then we have to shift the bit towards right side. So the 1 will be shifted here, this one will be shifted here, this 0 will be here, and so on.
So at the end, if we are getting 0 will be here, so the MSB bit is 1. So we will repeat this MSB bit 2 times, so it is double 1. So the first iteration has to be complete. Now moving toward the second iteration, so we have to again see the q and q minus 1. Since we are getting here 1 and 1, so whenever we are getting 1 and 1, so we do nothing, just shift the bit towards the right side. So this one will be here, this 0 will be here, this one will be here, and at the end this one will come 2 times. So second iteration has to be done. Now moving towards the third iteration, so check q and q minus 1. It is 0 and 1. So whenever we are getting 0 and 1, we have to perform AC equals to AC plus M. So after putting the values of AC and M, resultant we are getting here 101010. Since we are adding two 5-bit of numbers and resultant we are getting here 6 bits, so the carry bit will get ignored. Now again, since here we are getting 0 and 1, so after the addition we have to perform the arithmetic right shift. So this 0 will be here, this one will be here, and so on, and the final result we are getting here 00101 and 01011. So this is the third iteration we are completed here. So in third iteration, we are getting 1 and 0. So whenever there is a 1 and 0, so we have to perform again AC equals to AC minus M. So resultant will be 10111, and the Q0 will be same, which is 01011. Again, we have to shift all the bits towards the right side, so these bits has to be shifted towards rise, and at the end this one will come as a 2 times. So we are completed with the fourth iteration. Now at last, which is fifth iteration, here again we have to check the value of q and q minus 1 in fourth iteration, which is 1 and 1. So whenever we are getting 1 and 1, so we do not have to do nothing, and just we have to perform all the bits has to be shifted towards the right side, and this one will be shifted here, this 0 will be shifted here, and so on. So again at the end of the MSP of AC, we have to perform this one will be 2 times. So fifth iteration done. Now at the end we have to check the value of AC and Q. So the value of AC and Q will combine together will give the minus 17 in binary. So the result will be 1110 which is the 2's complement of the minus 70. So this is the final result we are getting here.